right, ladies and gentlemen, class recording has started. So, on Friday, we introduced the concept of work. And we said that when work is done to an object, what happens to its energy? It changes somehow, right? Could go up, could go down. That talks about different types of work, and we'll get to that in just a second, okay? All right, in order for us to do work on something, we have two requirements. What are the two requirements in order for us to do work or to change the energy of an object? You can look at your outline, or you can look at the screen for guidance, all right? Hannah.
Applying force.
We have to apply a force, and then what does that object have to do because of our force? It has to move, all right? So, in order for us to do work on an object, we have to apply a force, and then that object has to move in order for there to be work done, okay? We went through several scenarios on Friday, and we talked about, is this a situation where work is done? And we talked about it from two standpoints. We can identify if work is done in two ways. What can we look for to determine if work is done in a situation? Abby, what's one thing we look for? Okay. What does work do to the energy? Work changes the energy, okay? So, if we're looking at a situation, and my question to you is it work, right? That's the question on the test, or the question we're analyzing, right? Okay? So, there's two things we can look for. Jay, what's one thing we can look for? Does the energy change in this situation, right? So, for the pitcher, right? Does the energy of the baseball change because of what the pitcher does to it? Yeah, it ends up with more what? After he throws it. Speed gives it what kind of energy? Kinetic energy, right? The ball ends up with more kinetic energy because of what the pitcher does to it. So that's one thing we can look for. Was the energy of the object different at the end of the situation than it was at the beginning of the situation? The other thing we can look for is the requirements, right? Does the pitcher apply a force to the ball? Yes. Does the ball move because of his force? Yes. So we have force and we have distance. We can also look for that as well. Okay? All right. Good with basic definition-y stuff. Okay? All right. On Friday, we were looking at not this one, but this one, where we were looking at this ball on the platform and the steps and all kinds of stuff like that, okay? So in picture number one, we see that the ball starts at the bottom of the platform, and it says PE equals 0, and then at the end of this situation, it's up on top of the platform, and it says PE equals 30 joules, right? Did the energy of that object change in this situation? Well, how much energy did it have in the beginning of the situation, according to our picture? 0. How much does it have now? 30. Is that a change? Yes. Right? So that means the energy changed. So was work done when we lifted the ball from the bottom of the platform to the top of the platform? Absolutely. How much work was done? Well, how much did the energy change?
30 joules.
It went from 0 to 30. It's 30 joules different at the end of our situation than it was at the beginning of the situation. Therefore, 30 joules of work was done. Okay? The amount of work done is equal to how much the energy changes in our situation. Okay? Good with that idea. All right, let's flip our page over and let's take a look at these cards. Okay? I will tell you that answering these questions can be done in two ways. There is a math way we can do it, or there is a concepts way that we can do it. Okay? I'm going to focus more on the concepts because the math gets a little bit tricky, especially just because of the numbers, but concepts, we can answer it without doing any math at all. Okay? Sorry. We have to, like, you know, multiply something by 2, right? But hopefully we can do that in our heads. Okay. All right. Description says the figures, it should say the figures to the left, show a car at 3 different times as it drives along a road. Use this picture to answer the next 3 questions. Okay. Just without answering any questions or trying to answer any specific questions, if we just examine this situation, what's happening to this car here? Drew, go ahead. It's moving. What else is it doing as it's moving? It's getting faster. Okay? So, first basic question, is work being done in this situation here?
Yes.
Yes. How can we tell that work is being done based on the information that we've given? Elizabeth, go ahead. The energy is changing. Specifically, what type of energy is changing in this problem? Kinetic energy is changing. If an object is going faster, it ends up with more kinetic energy. There is a change in kinetic energy. Work has to be done on this car. Okay? Good conceptually. All right, now let's answer these questions. First is asking you about the amount of kinetic energy when the car is traveling at 60 kilometers per hour. The initial picture shows the car traveling at 30 kilometers per hour, and it tells us that it has a kinetic energy of 10 to the 6th joules. I'm going to rewrite that like this. 1 times 10 to the 6th joules, right? Because if we multiply anything by 1, it's itself. Okay? That's going to be important a little bit later on. All right, good for starters. Yes? Good? Okay. It's asking us about kinetic energy. Like I said, this can be a math problem, but let's turn it into a concept problem. What happens to the kinetic energy of an object as we go faster? It increases. So this car at 60 kilometers per hour should have more kinetic energy than it had previously. Okay? We learned and we discussed last week that there is a relationship between speed and kinetic energy. What kind of relationship do speed and kinetic energy have? A quadratic relationship, right? Parabola shape, etc., etc., etc. Okay? So, what has happened to the speed of this car going from picture 1 to picture 2 in this situation here? Drew? It has doubled, right? Going from 30 to 60, it means that the velocity is now twice as fast as it was before. Okay? So, in this case, velocity has increased by 2. Okay? If that doesn't make sense to you, write it in words, right? This car is going 2 times faster than it was before. Okay? Now, we can tell how much kinetic energy something has if we know the relationship. We said, what kind of relationship do velocity and kinetic energy have? Quadratic. Meaning, we have to do what mathematical operation here? What do we have to do with the amount that velocity is increasing? We have to square it, right? We discussed this with our Crocker-Park scenarios when we were introducing kinetic energy, right? If something goes twice as fast, how much kinetic energy does it end up with? Is it twice as much kinetic energy? No, it's 4 times as much kinetic energy. Because it's squared. That's important for the next question, right? So here, kinetic energy is not twice as big, it's 4 times as big. Because of the quadratic relationship. Quadratic relationship. So, If the kinetic energy of the car in picture 1 is 1 times 10 to the 6 joules, how much kinetic energy will it have now? 4 times 10 to the 6 joules. Oh, 10 to the 6 joules. Everyone see where that number came from? We really didn't have to do any math to solve that problem. We just got to know our relationships between. Yeah, I made the exponent j because I was trying to write my unit first. So. Okay. Good with that one. Okay. Very similar for this second question. How much kinetic energy will the car have at 90 kilometers per hour? In relation to the first picture, right? What has now happened to our velocity? Well, let's go back to our very first picture, right? How much faster is the blue circle than this first circle? It's 3 times faster, right? So the velocity has increased by 3 times, right? Kareem, if the velocity I saw you making hand signals that way, right? Okay, so if the velocity increases by a factor of 3, be confident, you have the right answer. How much does the kinetic energy go up by? 9 times. Because what do we have to do with our velocity in a quadratic relationship? We have to square it, right? 3 squared is 9. Okay? And again, that's from our quadratic relationship. So, how much kinetic energy should the car have now? 9 times 10 to the 6th joules. Because it's got to have 9 times as much energy as it had originally. Yes, no, maybe. Thumbs up, thumbs sideways, thumbs like halfway between sideways and up, maybe. Whoa, double thumbs up. All right. This gets back to how are speed and kinetic energy related to one another, right? We really didn't have to use our calculator at all here. We just have to know the relationships. Okay? All right. Ready to move on? Because the next part's a little bit trickier. Okay? The next part, okay, it says, when the car was traveling at 30 kilometers per hour, so pink circle, it had to slam on its brakes to come to a stop. And it said that it skidded for 15 meters before it came to a stop. Okay? First question. It doesn't say this question on the sheet here, but it's an important question for us to answer. Is work being done on the car when it slams on its brakes and skids to a stop? Negative work is being done. Okay? So in the pink circle, to bring the car to a stop, how much work do we have to do? Well, that's not the right answer. That's why I'm not going to ask you. All right. So, how much kinetic energy does this car have when it's traveling at 30 kilometers per hour? 1 times 10 to the 6 joules. When it comes to a stop, how much kinetic energy does it have now? When it comes to a stop, how much kinetic energy does it have now? 0. Okay? So, In the pink circle, a car driving at 30 kilometers per hour that has this much kinetic energy, when it comes to a stop, that much work has to be done. Does that make sense? Because work changes the energy. The car starts with this much kinetic energy, but it ends with 0 kinetic energy. So coming to a stop requires this much work to be done. Okay? Good. All right. Okay? The next part of the question says, now when it's traveling 60 kilometers per hour, it has to slam on its brakes and come to a stop. First, is work going to be done bringing this car to a stop? Absolutely. Its kinetic energy is changing. We've already established that when it's traveling 60 kilometers per hour, it has 4 times 10 to the 6 joules of kinetic energy. Yes? That was the answer to the first question on this page. Meaning, how much work has to be done to bring the car to rest here? Because even though it was going faster than before, if we bring that car to a stop, how much kinetic energy will it eventually have? 0. What? Are you okay with this or not? That's not what I had. I said yes or no. Those are your 2 choices. You can say no, because I'm pretty sure if you say no, you're not the only one who's going to say no. Believe you me, one thing I can tell, like when I'm looking at you guys, I can see what your faces look like. All right?
But some people are just
No, but some people look like this. They're like Katie. I didn't want to call Katie out, but before when I asked for a thumbs up, she gave me a solid thumb sideways. And if she could have, she probably would have given me this way, but she didn't want to go that route. Okay? So, and you know what? She's not the only one. Okay? So, let's talk, okay, first, do we understand that work has to be done to bring this car to a stop? Because we have to change the energy. Do we understand that the energy is decreasing when we bring a car to a stop? Are we okay with that idea? Do we understand that the final energy that the car has when it stops is 0? Are we good with all those things? Does it make sense where these 2 numbers come from then?
yes.
Okay? This is how much energy the car has when it's going 30 before it slams on its brakes. This is how much it has when it's 60 slamming on its brakes. Okay? All right. We didn't get to the how far part. This actually is important for one of your test questions, so you might want to wait until tomorrow to do that quiz. Okay? Because if you don't understand this question, answering one of the questions on the quiz might be difficult. Okay?
Oh, Jackson's that?
Okay.
What?
I mean, if, you know, joke of the day is kind of fun, like as a special thing, you know what I'm saying? If we do it every day, it'll lose its charm. You know?
But joke of the day is called joke of the day.
That's true.
I voted 10%. I don't want to look up it.
All right, that's cool. Like, I see where we stand, Zach. We're not worth 10% of your phone's energy battery. I get it. I understand. All right, everybody. I will see you guys tomorrow, and we'll finish this up.